Okay, so today we're going to talk about some very interesting stuff and exciting stuff, maybe stuff which are completely different from what we practiced so far. Um, let's do a recap. With the help of learning by doing C++ video series, we sort of gained a basic understanding of semantics, sort of syntaxes or features of C++ as a programming language. Or maybe also we gained a little bit of knowledge indirectly about C programming language being the greater cousin of C++ with sort of 10 years of age difference. But at the end of the day, what we basically learned was basically to use those features to write our own applications. And we tried this in our channel in implementation of Rungekuta, for example, for solution of coupled ODEs. So no matter whether it's going to be that simple Rungekuta implementation in C++ or it's going to be any sort of computing task that might be interesting to you. But what we tried essentially was something which is called as sequential programming. And that means that we were dealing with things one task at a time. So we had a collection of tasks, and then we passed them to the computer, and then the computer was trying to execute them one by one until every task is successfully finished. Or the computer basically throws an error and says, hey, I tried to do my task that you assigned me to, but then this and that happened, and then I couldn't achieve that task. You're going to realize that if we try to scale our problems, so let's say if you're interested to know the dynamics of like hundreds of thousands or probably millions of charged particles in an electromagnetic field, or if you're interested to do some CFD analysis for fluid flow around sort of a large aircraft, to compute the drag coefficient, to see what is the flow pattern around the wings or stuff of that nature. So you're going to realize that you're going to be soon in a deep trouble. The first problem you're dealing with is probably the memory. Your personal computer, like my sort of laptop here, probably is not going to be enough to load all the necessary data structures which are needed for such a simulation, for example, for an aircraft. But let's say memory is not an issue. Let's say you have access to infinite amount of memory on your laptop. Then performing that task, doing those computations is going to take ages on your personal computer. So now you're going to realize the essence or the need of something which is called as distributed computing. So in contrast to sequential programming, we're going to have something called as concurrent programming. So we're going to use the sort of help of parallelism to achieve a task, a computational task. So this is sort of the subject of what we're going to talk about in these video series called as Learning by Doing MPI. So before talking about MPI, let's draw an analogy with humans. So when humans are going to work in big teams, in large teams, you know that, for example, one department works and creates some results, and another department relies on the results of that department. So there needs to be some communication and flexibility between the different teams that are working in a general big team to achieve a task. So the same way, so we draw that analogy to also be true for computers as well. So we are going to use, instead of our own personal computer, we're going to use hundreds of computers. Or we're going to use, for example, thousands of computers to achieve a computing task. But if we want to do so, we need to do some communication, because each sort of computer or each distributed computing unit doesn't have information or doesn't have knowledge about other people or other machines, sort of things that they computed or things that they have in their memory. So we got to do some communication. And when you're talking about communication, you need something such as MPI, which basically, it's perfectly coming into this picture. Message passing interface. It's sort of a standardized and portable library which gives you sort of this ability to communicate with the distributed computing units that you have in your network of computers. So those computers, of course, need to be connected with those InfiniBand, network cables, so that they can transfer information as fast as possible. So that's MPI. It has a standard committee, and the standard committee sort of lays down the foundation, or sort of the general protocol that needs to be how do we say it needs to be followed in order to do those communications between those distributed computing units. But there are different sort of implementers. There are different implementing vendors such as Open MPI, MPeach, or other libraries that they basically take those principles and they apply them into their own libraries, and then you can use those libraries. So this is the subject of today's video. We're going to sort of compile Open MPI from source, and you're going to do it, you're going to see every step basically. So right now in my current directory, I have OpenMPI 4.1.6 tar.gc. So I'm going to do the task behind the scenes because this takes a while, and then we're going to talk about other stuff. So I'm going to extract this thing. Then I'm going to go to the directory. All the install sort of guides are in this very short document. I encourage you to read this thing. And if you're working with specific hardware, or if you need some specific sort of command line flags and stuff like that, then you got to go to README because it has all the information about those stuff. Anyways, so we're going to say configure, but before doing this step, we need the installation directory. So here I'm going to say installed directory, and then I'm going to take the address of that directory, and then coming back to OpenMPI, I'm going to say configure with prefix of that. This is the custom installation directory that I'm interested in. So since I'm working with Mac, you know that GCC on Mac basically is a wrapper for Clang. So I don't have access to G-Fortran. So I don't need basically, I'm going to say disable MPI Fortran. I don't need the MPI binding for Fortran, the Fortran binding basically. So I'm going to hit the return key. This thing is going to take a while. So meanwhile, I'm going to show you some other stuff. This thing, you see that behind the scenes, it's doing its magic. So we're going to say MPI standard. Standard. So the first link is basically the standard. So we have MPI 4.1. You can read this thing. It's a PDF document. It's a over 1,000-page document. You see it's pretty also new, November 2nd, 2023. But in order to download this thing, you cannot download it from, this is the MPI sort of forum, but you need to go to OpenMPI. And here the first link, in the download section, you're going to see that the latest version is 5.03, but you know that, it's probably not a good idea to always work with latest and greatest, because usually the code bases that you're working with are, a little bit left behind. There are some old code bases that maybe they're not fully compatible with these newer standards. So a rule of thumb is that probably work with the older versions. So this is the version that I have downloaded. This is exactly the tar.gc that I have downloaded. If you click on this, it's going to download it for you, and then make sure that you check MD5, SHA1, and SHA256 to see whether you exactly downloaded the same file that they put on their sort of servers. So this is OpenMPI. This is one of the implementers of the MPI standard. And actually, this is fairly new. It's not that old, let's say. So MPI 4.1. That's why we're not working with 503, because, might be problematic for us in the long run. So you can see the background, for example, on MPI 4.1. It says, this thing is finished, I think. Yeah, it is. So you can see that the version is 4.1.6. We have C bindings. C++ bindings are deprecated. I think as part of MPI 2.2 or MPI 2, somewhere around there. We don't have any more bindings for C++. You can use the same bindings for C as a C++ programmer. Fortran bindings, of course, we don't have them because we explicitly, we sort of disabled them. And that's it. So now I'm going to say make all. This is, if you've paid attention to the Runge-Kutta series, we had those build systems. We worked with make before. So if you say make all, it's going to go and compile everything. It's going to call those GCC commands and other compiler commands with proper flags to compile everything for you. But since it also supports parallel sort of compilation, I'm going to pass in -J8 to use sort of 8 processors to do so. This thing also is going to take some time. So maybe we can go back to our MPI standard document. So it says that MPI 4.1 is a minor update to MPI standard. So this is probably relative to MPI 4. Yeah, it says here, it contains mostly corrections and clarifications to MPI 4. And now if you go back probably to MPI 4, yeah, here it says that MPI 4 is a major update to MPI standard, of course. So major updates, you know, it works with the first digit. So usually that's the case. And then the second digit is when you have like corrections, clarifications, and stuff like that. So this document is going to be super, super important to us. If you take a look at, I cannot basically find that list again. Okay, this is the tables. Let's go back. So we're going to have basically everything that we need in this document. And it's a pretty sort of extensive document. I'm sorry. So we're going to have like, you know, terms and conventions. We're going to have point-to-point communications. We're going to have partition point-to-point communication, then data types, collective communications. So this document is quite exhaustive and quite sort of expressive in terms of everything that you can perform with MPI in general. So we're going to use basically this document in these series of videos that I want to make, basically learning by doing MPI, or message passing interface. So make sure that you download this document. So I think this thing is finished. So now if you say make install, it's going to install whatever basically it was trying to compile in the previous stage. So at this stage, it's going to take all those sort of compiled files and take them into that installed directory that we defined in the beginning before the configure step. I'm going to keep everything basically here because I don't want you to think that there's some dirty magic happening behind the scenes. So you're going to have everything. You're going to see every step of the way. So if I go to my installed directory, so you're going to see we have some some bin directory, some libraries, which contains all those dynamic libraries or shared objects on a Linux system, those dynamic libraries. So right now, if I say MPI run -- version, you're going to see that it says, hey, MPI run command not found. And that's because we are not using proper sort of, we haven't added these addresses of bin and library and stuff like that into our environment variables. So this is what we want to achieve right now. So I want to say export. The first thing is path. So this is the installation directory. So I'm going to say bin, that's the binary directory. Then I'm going to pass in path. So this is the first one you need to do. Then the second one is ld library path. It's going to be the same, but lib. And then ld library path. And then the third one is going to be, I'm going to use this one, pkg config path. Then I'm going to go back. This is going to be config, and this is going to be package. So right now, if I say MPI run -- version, since I have this path now known at runtime, then it should work basically out of the box. and you can see that we have MPI or Open MPI 4.1.6. So this is, of course, is going to be temporary effect. So if I close this sort of terminal and open a new one, it's not going to work anymore. So if you want a permanent effect, and of course that's something that you want, you're going to go to your .bash profile if you're working on a Mac operating system and add exactly these 3 lines to there. Or you're going to work with your bash RC if you're working on a Linux operating system. So add these 3 lines and then you're going to be good to go. So let's test our Open MPI. I'm going to go to my compilation from source, and here I have a sort of test.c application right here. I'm going to say MPI. I'm not going to show the content of test.c because that's going to be the subject of our other videos. So for now, we just want to see whether our Open MPI works with this very simple program written in parallel form. MPI-CC. By the way, MPI-CC is sort of a wrapper around your C compiler. If you take a look at the previous videos that we made, for example, when we were talking about build systems, about make, CMake, and stuff like that, then you should remember that each sort of compilation step required us to say G++, and then we had to say, for example, -I, and then give the directory to that specific header files if they were not in the project directory. Or we had to say, for example, -L to give the address of the libraries if they are not sort of stored on a standard location in our computer. Or -small letter l to name the libraries that we want to link to our binary file. So MPI-CC basically does everything behind the scenes for you. So it's going to do that -I, -L capital, -L small for you to import all those basically libraries or header files that are needed in your application. So it's just a compiler. It's a wrapper for the GCC, and it has those convenient flags for you. So we're going to say test.c, MPI-CC test.c. If you do that, now we're going to get our executable. So I'm going to say MPI run -np. So this is the number of processors that we want to use. We say 4 processors on our machine, and then we say a.out, similar to executable that we had in a sequential programming form. So if I hit the return key, hopefully it's going to generate an output for me. Otherwise, I'll be disappointed. And by the way, this is taking some time. The reason for that is because I have Safari with hundreds of tabs open. I have Google Chrome with 200 tabs open. And I'm recording also at the same time with QuickTime. So that is why it takes too much time. Otherwise, if you probably try it on your machine, it's going to be much faster. So you see hello world from 4 different processors, processor number 1, 2, 0, and number 3. So if I say MPI run -np20, because my machine doesn't have 20 processors, and if I say a.out, you see that MPI is going to complain. It's going to say, hey, you don't have enough slots for that. You don't have 20 sort of processors. So it says alternatively, you can use oversubscribe option to ignore the number of available slots when deciding the number of processes to launch. So this means I can say MPI run -np20, and then I can say oversubscribe, and then I can give a.out. If I do that, you see that I immediately get sort of everything here on my single machine with, I don't know, 10 cores or so. So sometimes if I increase this thing a little bit more, something around 30, for example, you see that this thing is not going to work. And it says that, hey, a system call failed during shared memory initialization. And then if you look further, it says that, hey, somewhere Vader segment. So Vader is one of those BTLs, so one of those byte transfer layers in MPI. So you can exclude this thing if you want to basically get rid of this error. So MPI also comes with MCA, which is, I think, modular component architecture, something like that. You can pass in some sort of command line options. You're going to say MCA and you're going to say BTL. So now I'm going to exclude with this hat, I'm going to exclude the Vader. And then I'm going to do, so it comes in pairs of keys and values. So BTL is the key. So that's the byte transfer layer. And then the value is exclude the Vader from that. So now with 30 processor and oversubscribe, if I hit the return key, you see that I don't get that error anymore. So that memory initialization error is gone. So there we go. You have learned how to compile OpenMPI from source. I hope you learned something from this video and hope to see you in the next one.